I will show you some applications of molecular docking, virtual screening, and molecular dynamics simulations. Okay, so I will just try to show you that thing. And so basically this will be some applications, and since everybody is working on SARS-CoV, okay, on COVID-19, so I will also show you some examples from SARS-CoV-2 virus. Okay. The first we'll talk about the interactions between these 3-cell proteins and 2 inhibitors. Okay. So this inhibitor actually, okay, figure B that is shown. So that paper was published in the magazine Science, and we will try to understand what are the different interactions that control the binding. Okay, and using that we can of course modify the inhibitor further and make it even more potent. Okay, so that would be the objective. So now, why do we need to do computational study when it is already started experimentally? When the crystal structure of the protein in complex with the ligand is already available, and you know that by inspecting the 3-dimensional structure of the complex, you can deduce the mechanism of binding. Then why do you need molecular modeling? Okay, well, you need it because you are missing something in experiment. One of them is the solvent effect. Okay, I said that generally, I mean, all of you know that all the proteins or any biological macromolecules, they reside in some kind of solvent environment. It could be aqueous environment or it could be membrane environment. But when you resolve the crystal structure of this protein ligand complex, at that point, this is a soluble protein, okay, but you are not considering the solvent. You are solving this crystal structure in a buffer solution. Okay, so that means you are really not mimicking the exact biological environment. So we want to conduct MD simulations to include the effect of solvent in the binding process. Okay, the second of all, from experiment, I mean from the 3-dimensional crystal structure, you can see only whether there are some hydrogen bonding are there or not, or whether there are any van der Waals interactions are there or not. But how do you quantify them? So you say that, okay, that this is the, say, minus 10 kcal per mole is the binding free energy. That thing you can get it from the experiment. But the question is, so of this minus 10 kcal per mole, what is the contribution from the van der Waals interactions? What is the contribution from the idiostatic interactions? What is the contribution of entropy? Those things are missing. Okay, that you cannot get from experiment. So we perform molecular dynamic simulations to bridge this gap. Okay, so simulations are performed not to replace experiment. No, simulations are performed to complement the experiment. Okay, so we not only include the effect of solvent, we calculate the binding free energy, and then we decompose the binding free energy into different components of van der Waals, idiostatic, all different parts we decompose it. Otherwise, which is that you cannot get it from experiment. Okay, so that's why we perform molecular dynamics simulations or molecular modeling. So the question is, what are the different ways you can calculate binding free energy? So at the very beginning, I mean, first 2 lectures, basically I talk about the docking. Okay, virtual screening, I said that is the lowest accurate, and then the docking is better. So this figure actually shows you that how the accuracy and speed are inversely proportional. If your method is very accurate, then the speed is the lowest. And if you want to increase the speed up, then you will lose the accuracy. So the free energy perturbation or thermodynamic integration, that is the most accurate computational technique available to us to compute the binding free energy, but it is very computer intensive simulation. You need large computational resources for this one. And docking is a very fast method, but it is also least accurate compared to other methods. There is another method called LI, okay, linear interaction energy method, which is better than docking. It is fast also, but the accuracy is not up to that level. Okay, so I said that from virtual screening, you reduce the number from millions of compounds to say hundreds of compounds. And then from docking studies, you further reduce the number from 100 to 20. Now, the question is, how do you reduce the number from 20 to 5? Or you want to get the exact ranking of this 20 molecule, which one is the best molecule? Because whatever you are getting from docking, you really cannot trust those results, okay? Because there are some error associated with it. And if the difference in energy between two ligands is only, say, minus or maybe say 0.5 kcal per mole or 1 kcal per mole, then how would you differentiate? Okay, if the error is too high in docking. So that's why we need to use a better method. But at the same time, we also need to keep in mind the speed up. So now considering the speed up and accuracy, the most popular method that is frequently utilized to estimate the binding free energy is called MMPBS. Okay, so where MM stands for molecular mechanics, PB stands for Poisson-Boltzmann, and SS stands for surface area. Okay, now the Poisson-Boltzmann equations that you have encountered, of course, as a physicist also you have encountered, and in mathematics also they encounter, because this is a nonlinear partial differential equations. And you know that, I mean, solving this nonlinear partial differential equation is not that easy. That becomes numerically very unstable. So we make some assumptions and we convert it into a linearized equation. Okay, so we solve LPB, linearized Poisson-Boltzmann equation, that is given here. Okay, so that's the basic thing, and this tells you what is the mechanism. I mean, the workflow of MMPBS scheme. So we start from the complex structure. Okay, that means we know the crystal structure of the protein and the ligand. If the experimental structure is not available, then we will do the molecular docking to make the complex. Okay, so once you have the complex structure, then you immerse it into a box of solvent. If it's a globular protein, then you have to put it in the water. Okay, and then you perform molecular dynamic simulations. So in molecular dynamic simulations, you got a trajectory. Trajectory is nothing but an ensemble of conformations. Because I told you that during, in the morning, that we store all the positions, okay, XYZ coordinates, each time step. So that is the conformation, okay, XYZ coordinate that determines the structure, and we call it conformations. So you have the time evolution of the conformations, okay, so that is called the trajectory. So first you remove the solvent, okay, water molecules from this trajectory. Then what do you have? You have a dry complex, okay, which is devoid of any water molecules. Now from these complex conformations, you can remove the coordinates corresponding to the ligand. Then you will have only receptor part, okay, that is the protein part. And if you remove the coordinates corresponding to the receptor, then you will have coordinates corresponding to ligand. Okay, so that means from the single trajectory simulations, you can have 3 trajectories. You can generate receptor, ligand, as well as the complex. Okay, now we use very simple thermodynamic equations to calculate the binding free energy. So delta G bind, okay, that is the binding free energy is equal to, you have to get it by subtracting the free energy of receptor and ligand from the complex. Okay, Now, for each reactant, the binding energy is H minus Ts, where H is the enthalpy, T is the absolute temperature, and S is the entropy. Okay. For in molecular mechanics, H, that is the enthalpy, is sum of molecular mechanical energy and solvation energy, and then T times the configurational entropy. Okay. So here, what you are doing basically in molecular, this MMP-based scheme, you are combining molecular dynamic simulations and a free energy scoring scheme to get a free energy of binding. So that means you are performing NDIP simulation to take into account the effect of solvent as well as the dynamics part. I told you that when you dock the structure, okay, or if you start from experimentally determined structure, those are nothing but a snapshot. It's a single conformations. But proteins are flexible molecule. Now, during the docking process, you only let the side chain of the binding pocket residue only to fluctuate. That is also just via rotamer library that you have observed it yesterday. Okay. But I said that you cannot take into account the effect of backbone fluctuations. For that one, you need to conduct MD simulations. Okay. So that part is taken care of. And now you need to score it. I told you that the accuracy of any docking software depends on two aspects. One is the scoring function and the other one is the searching algorithm. Okay. So scoring function generally in molecular docking, they use a heuristic method. Okay. So those are generally knowledge-based scoring function. It's not physics-based. Okay. Those are knowledge-based things. So that means there is some error. So now, when you perform molecular dynamic simulations, so I have shown you already that potential energy function. Okay, so that 5 different terms. So that's the physics-based terms. So it is more accurate. We will utilize that equation to evaluate the energy. Okay. So that way you are ensuring the accuracy of your result also. Okay. And now, since you have a trajectory, so that means you are considering an ensemble of conformations to evaluate the binding energy of each complex. Okay, for each complex you are conformations you are evaluating it, and then finally you are making an average. So that is even far better than getting it from a single conformations. Okay, so you get an average energy basically. So that is the best thing. Okay, that's the advantage. And remember here one thing. So first, when we perform molecular dynamic simulations, we consider explicit water molecules. That means the water are also treated at the atomistic level. That means water has 3 atoms and we are assigning charge to each atom and the bond lengths, everything we are assigning. Okay. Now, when we use MMPBSA, when we use Poisson's-Boltzmann equation, that is an approximation of the solvation effect. At that point, you are not considering any explicit water molecules. You are treating water as a dielectric medium, okay, which is characterized by epsilon is equal to 80. Okay, so that means initially when you conduct MD simulations, your protein is in a box of solvent. When you are evaluating the free energy and using PB method, Poisson's-Boltzmann method, then there is no water molecules. Rather, your protein is the complex is in a dielectric medium. So there will be a boundary that will separate the protein from the medium. So now proteins are composed of a bunch of atoms and each atom has charge. So basically the problem boils down to a bunch of charge resides in a dielectric medium. So what will happen? There will be a polarization effect, no? So on the surface or the boundary of this protein and the media, there will be a charges on it. Those are polarizable charges, okay? So that's why this energy that you get from by solving the Poisson's-Boltzmann equation, that is called the polarization free energy. Okay, that actually takes into account the effect of solvation. And there are some parts of it. Okay, just let us talk here. So the molecular mechanical energy, so which is sum of the 5 different terms I told you, the sum of bond stretching, that is the first term, then the angle bending, second term, then dihedral angles, so that is the third term. Fourth term is the Lennard-Jones potential, that is the van der Waals interaction, and the fifth term is the electrostatic interaction, that is Coulombic interactions. Okay, so those are the things. The internal energy or molecular mechanical energy. Now the solvation energy has 2 parts. One is the electrostatic part, and the other one is the non-polar part. The electrostatic part, you model it by Poisson's-Boltzmann equation. That I told you that there will be a bunch of charges are kept in a dielectric medium, so definitely they will induce some polarized charge on it. Okay, so there will be dielectric response. So that's why that energy that you get is called polarization free energy or the polar solvation free energy. But at the same time, you have to remember one thing. If you want to put a solute in a solvent, what you need to do? You have to carve out a space to accommodate it. That means you are displacing the water molecules so that you can accommodate the protein. Okay? So now you are displacing those water molecules, it means there will be some entropic cost, penalty. Okay, so that part basically non-polar and also the hydrophobic effect also, or the dispersion term basically that we can say. So that thing you take into account by the non-polar solvation free energy, which is, again, we treat it in a heuristic manner here. So we say that the non-polar solvation free energy is estimated by multiplying the solvent accessible surface area with the surface tension coefficient. Okay, so that way. Now the question is, so these are all actually easier to do. The main problem is how do you estimate the entropy? Because that is the most time consuming part. Now, entropy is very important because when protein and ligand or any biological molecules and the small molecules are before the bind, both can rotate, vibrate, or translate. Okay. Now, when they bind, then they lost these 3 different degrees of freedom. So that will cause some entropic penalty. And entropy always disfavors the complex formation. So you have to take into account. If you don't take into account the entropy, then you will get a very high negative energy and you will think that, oh, this compound gonna work on it because I got a compound which binds very, very strongly with it. Well, you have not taken into account the effect of entropy. So entropy is very important. So since there are 3 degrees of freedom associated with it, so there are 3 components of the entropy. You have to calculate individually all those 3 components. Okay, the rotational component and the translation component that you can get it from Wittgenstein approximation. That is actually easier to do it. But the main thing is the vibrational entropy that you calculate from the normal mode analysis. So normal mode analysis, again, it is a machine learning approach. Okay, I mean, these days people call it machine learning, but this is a very old method. I mean, we use in classical mechanics, everybody reads these things in their MSc syllabus. In mathematics also, I believe they read it, okay? But people now these days call it machine learning approach. Anyway, so normal mode analysis, then we perform to get the vibrational frequency, and from that vibrational frequency, we can estimate the vibrational entropy, okay? So that is the method. So the first system I said that I'll show you this thing. This is our first example that I'm going to show you using this approach, how we can study these things, okay? So we perform this, we get these structures, the complex structures from the protein data bank, okay? The PDB IDs are 6Y2G and 5R84. And the protein, we model it using the AMBER 14 Stony Brook force field. And then the ligand force field, okay, I mean, for any kind of molecular dynamic package, the standard residues phosphoryl parameters are there, but for ligands a small molecule, so their parameters are not available. You have to generate your own parameter set for that one. Okay. Now the parameter for the protein parameters, I told you that those are generated using the quantum mechanical calculations. Okay. Generally, they performed DFT calculation, density functional theory calculations. Now, for the small molecule, for the ligand also, you should follow the same protocol. Okay, but it is very time consuming. So that's why instead of using the classical mechanical approach, the quantum mechanical approach, we use a semi-quantum mechanical approach. Okay, so this is for that one, we use a different set of Hamiltonian here. Okay, it's called AM1, Austin Model 1. Okay, so that is the Hamiltonian we use, and then we do some bond charge correction. Okay, so that's why this method is called AM1 BCC. That's to assign charges to each atom. Okay, now that is for charge assignment. Now you need to know the mass of each atom and also the bond information. So that for that one we use this generalized Amberg force field, okay, GAF2, the updated version, so on we use. And water molecule, we have to model it, okay. For that one, we use the model T3P model. There are various models available, T3P, T4P, T5P. So T3P means basically 3 point, okay. The water basically this H2O, no? So 2 hydrogen and 1 oxygen. So basically these 3 points you just use as it is. And then I said that the isostatic interactions are long range in nature. So, and it is also pairwise. You have to consider all possible. Now, this is a big protein, so if you consider all possible interactions, then your simulation will be hampered. So here we use, to take into account this effect of long range interactions, we use particle mesh UR scheme. Okay, so we say that okay, any atoms which is within 10 angstrom, we will compute it via direct interaction mechanism. Okay, for those we will use Coulomb-Singh interactions, and beyond that we'll treat it using this particle mesh UR scheme. That's a different summation scheme. Okay. And then we run this simulation for 100 nanoseconds, and then whatever trajectory we got it, then we do the MMPBSA calculations for that one. Now, since the formula, all this delta G is equal to H minus Ts, these are all equilibrium thermodynamics, okay? So we need to make sure that our simulation has converged. So one of the way to check that your simulation has converged, you need to find out the deviation of your starting conformation, okay, with the time how it is evolving, how much it is deviating from the initial structure. So that is called root mean square deviation or Rmsd, that is shown in A. Okay, so you see that after 40 nanoseconds, you almost have reached to plateau region. Okay, so the red cap corresponds to APO. APO means there is no ligand, only the receptor protein you are simulating. And complex one is basically the protein with ligand 1, and the complex 2 is protein with ligand 2. Ligand 1 is this alpha ketoamide 13B. So now that's you see that after 40 nanoseconds you achieve good convergence of your trajectory. That means the proteins are not deviating further. Now what about ligands? I said that MD simulation is required because when you drop the ligand in the binding pocket, it does not remain static. It still moves around it. Okay, so that you can see if you look at figure B. So initially, if you look at the blue curve, okay, initially you got an Rmsd even below 0.5. Then after 25 nanoseconds, suddenly there is a jump and it reaches to the value of 1.4 angstrom. So on the right hand, I have shown the probability distribution of these things, and you can see that both these conformations are equiprobable. So that means at equilibrium, your ligand can have both the structures possible. Okay, so these two corresponds to two different orientation in the binding pocket. But in principle, you want to have a single dominant conformations that will form the maximum number of interactions with the receptor. Now, if you look at the green one, the alpha ketoamide 13B, so this one is reported in Science. For that one, you can see that initially you started from 0.5 angstrom, it reaches more than 2, but it got stabilized. After 50 nanoseconds, it got stabilized. And that's why the distribution of it is characterized by a single peak. Okay, so of course this would be better. It is not moving that much. Okay, so it means that it also signifies one thing, another thing basically, that you started from the experimentally determined structure. So you thought that that is the best thing. No, actually it is not. So in experiment, whatever they got this structure, actually that is not the energetically more favored position. The energetically favored position is this one. That corresponds to an Rmsd of 2.5 angstrom. Okay, so that is the most dominant conformation the ligand adopt in the binding pocket. So now to find the dominant conformations, you can also do another this support vector machine approach you can take, or this this is called K-means clustering approach. Okay, so that will give you what are the dominant conformations for alpha ketoamide and these things that you can see. Okay, now another interesting thing we want to look at is the dynamic cross correlation map. So we want to see when a ligand binds to a protein or any biological macromolecules, okay, or it could be nucleic acid. So what happens to the atom of the receptor, how they are behaving, how they are moving, whether they have correlated motions or whether they have anti-correlated motions. For that one, we calculate this dynamic cross correlations. Now, figure A corresponds to the apo structure, okay, that means there is no ligand in it, and B and C corresponds to when the two ligands bind. Okay, so now if you compare A and B, okay, in A I have shown one black circle. Okay, so now look at it. This color scheme, just want to tell you that the red one is the negative value. Okay, so that is the negative value corresponds to anti-correlated motions, and the positive value corresponds to correlated motions. Okay, and the cyan color corresponds to neutral motions. Okay, I mean there is no correlation actually. So now if you see that in region R1, you still see some red patches actually there. So you see some anti-correlated motions. But when you compare A with B, okay, just look at that black regions. What you see, it becomes yellow and greenish. So when the ligand binds, the amino acids in that region, they have a concerted motions, and it is correlated motions that enhances the binding phenomenon. So now if you look at the R2 region in B, okay, figure B, and compare it with A or C, you can see that in B actually it is reddish, okay, that is anti-correlated. But in A, which is apo structure, it is bluish. So that is also anti-correlated, but after the binding, it becomes red. It means the anti-correlated motions in that region increases. Okay, and the region R1 actually corresponds to the binding region. Okay, so there you got correlated motions when the ligand binds. Okay, so this way you can get a lot of different kind of informations that can tell you the underlying atomistic motions due to the binding of different kind of ligands. Okay, so they can induce different kind of motions. So how they are varying, that kind of information you can get it. The next thing is another approach. This is also an unsupervised approach, okay, machine learning approach, which is very much used in physics. This is called a principal component analysis or PCA analysis. Okay, so if you perform this PCA analysis, so for figure A, that corresponds to APO structure, you see that you got two minima. Okay, the minima corresponds to the dark blue. So those are the favored region. So it means that at room temperature, these structures have two different conformations. Now, which one you should target to develop dark? Of course, you should target the one which is the most probable. So this shows the importance of conducting MD simulations, okay? Because it helps you to identify the real structure of the drug that can be, excuse me, I got a call. Can I just receive a call? Just a minute, okay?
Sure, sir. Sure, sir.
Second, I got one call. I'm extremely sorry. Actually, I got a call from academic office because Saturday my exam paper is there. Okay, so that's why they are asking for questions paper and all those things. Anyway, let's get back to the business. So that is the utility. Okay, so if you just take the raw crystal structure and try to develop a drug, sometimes it could be wrong. Okay, because you are not targeting the most probable structure. If the protein is very flexible, so it can have multiple conformations at room temperature. Okay, and X-ray crystallography gives you a snapshot of only one structure. So if you target that, it may not be the most probable structure. Okay, so if you just do first MD simulations and find out what is the most probable structure, and using that you try to dock and develop new drugs, that would be the best strategy. Anyway, so now you see that when the protein is in a free state, okay, there is no ligand, it has two minima. But when alpha ketoamine, that's 13B, binds, then you see that the total sampling space become narrower and there is only single minimum. Okay, so that means the ligand binding gives stability to the protein. Okay, and if you look at C, that is for the when the second ligand binds, which is a little bit small ligand and which fluctuates a lot, that I have shown you that it can have two different conformations when it is bound. So for that one, actually you got two different minimas, and the most probable has 61% and the other one has 39%. That's why this is not a good drug actually. So the B1 works better. Okay. Now on the extreme right, I have shown again ABC figure with a porcupine plot. Okay. And the porcupine, you know that they have this spike. So that is the thing I have shown here. So basically this spike or the porcupine that shows the direction of the motion of each atom. Okay, so the principal component that you get by constructing a Hessian matrix and then you diagonalize it. Okay, the eigenvectors are your mode, okay, or the principal component, and the eigenvalues are the basically the fluctuations, basically how much it can. So the length of this porcupine tells you how much they are fluctuating. If it is small, that means that portion is not fluctuating much. If the porcupine, this green spike that I have shown you, if it is more, that means those region is more fluctuating. So you can see actually in A, which is APO, when there is no protein, so which are the in which directions the atoms are moving, and when the ligand 1 is bind, you can see how the motions are changing. So this kind of thing you can actually look at it at the atomistic level from this kind of analysis. Okay, so that's one thing. Now, so principal component is fine, but that is only used to study the conformational change in globular structure at the global scale, but you know that for protein actually the structural changes, there are, if you take any internal coordinates, that is the better way to study the conformational change. So one of that internal coordinates is the dihedral angle, because whether it is a alpha helix or beta sheet or coil, that is determined by the phi side plot. Okay, that is the dihedral angle. That's what Ramachandran did it, and it's unfortunate that he never got the Nobel. He was one of the Indians who should get the Nobel Prize. Okay, it's very sad that he didn't get it. Anyway, so dihedral is one of the internal coordinate that we can use to study at great detail what could be the further if there are any other structures that this protein can adopt. But mainly we utilize it to study the dynamics of the loop region. Why? Because loops are very flexible. So whatever the loop structure that you get from experiment, okay, from X-ray crystallography, that is not correct actually, because loops are so flexible that you don't get their good electron density. So in many cases, you will see that if you look at the experimentally determined structure, you will see that they omit the loop region because they could not get the electron density. So how to construct it? So that means loop can have multiple conformations. So that exactly we study, and for that one we use dihedral principal component analysis. Okay. So now the same thing we have shown. A corresponds to the free state. Okay, there is no ligand bound to the protein. So there you can see that there are two conformations possible. The global minima, basically there is one global minima which is represented by 70% of the structures. But there is one more minima is there. Okay, that's a local minima, not a global, that you can see. It's not dark blue actually, but that is represented by 30% of the structures. Okay, now when alpha ketoamide binds, then you got two distinct conformations, which actually equiprobable conformations. This loop can only have. Okay, I have shown this loop actually plotted on the right hand panel. And for C also you see that multiple conformations possible, 46%, 41%, 13%, all these things. So basically here we have performed PCA analysis and then we perform k-means clustering to get the different percentage actually. Okay, so this actually helps you to design your drug, okay, because you know that, okay, this is the most probable conformation, so I should target to develop drug accordingly, okay, because it tells you the orientation of the side chains of the amino acids. So that's one thing. And then finally, we calculated the binding affinity of these two ligands using MMPPSA, and then we compare with two HIV drugs, lopinavir and darunavir. If you remember it, that when this SARS-CoV-2 breaks out, then people say that that HIV drugs could also be used, and many people claim that they have used it successfully. Okay, although it is not that successful anyway. So exactly that you can see that if you look at this bar plot, you can see that the alpha ketoamide has a more negative binding affinity. Okay, so that means it binds more stronger compared to the another drug. Okay, that is represented by G3179268. So that is the ID actually, zinc ID. Okay. So now this figure is very important, and if you just basically this table is represented in the bar plot. Okay, the same thing. Now if you look at it, the question is why alpha ketoamide 13B is more potent, or why as it have a better binding affinity compared to Z31792168. Why? Okay, we go ahead and decompose the binding friends into various components, van der Waals, isostatic, polar, non-polar, solvation, and we have shown it here. Now, if you just look at the first bar, then you can see that the red one is much negative than the cyan color. Okay, so that means that is also more favorable in case of alpha ketoamide. Similarly, the isostatic is also more favorable in case of alpha ketoamide. But look at the polar solvation energy. That always disfavorable because that is positive. Okay. Now for alpha ketoamide, the polar solvation energy that you get by solving Poisson's-Boltzmann equation, it is more unfavorable compared to the other one. But again, the non-polar solvation energy, okay, that you get from the solvent accessible surface area, that is more favorable in case of alpha ketoamide. And the entropy which disfavors the complex formation, they are more unfavorable for alpha ketoamide than Z3179-268. Okay, so if you just all sum these two together, then you can say that the drug binding is mainly favored by van der Waals and isostatic interactions. Okay, now the polar solvation energy, I said that is also actually isostatic in nature because you are getting it from the polarizable charge. So that is also charge-charge interactions. And then there is Coulombic interactions. That is delta E elect. Okay. Now, since both of these two terms are isostatic in nature, you can sum these two together. Now, if you look at the table and look at this delta G pole plus elect, okay, you see that for alpha ketoamide it is 27.71, that is positive. And for Z3179-2168 it is also positive, but it is half, 13.44. Okay. So, although the intermolecular isostatic interaction is favorable, but the net isostatic is unfavorable to the complex formation for both cases. So you can safely say that here the binding is mainly driven by the van der Waals interactions. Okay. Now you look at it. Alpha ketoamide is bigger than this Z3179-268. So that's why it fits better in the binding cavity and it can have more number of van der Waals contacts with the receptor. That's why it has a better binding affinity. You need to basically understand these things. Just by increasing the number of hydrogen bond, you can have a good isostatic energy, but you are increasing the delta G pole also. And together they will, if they becomes positive, then there is no point of making more number of hydrogen bonds. Rather, you should look into how to optimize the non-polar interactions. Okay, that is the van der Waals interactions. But you should also remember one thing. If there is only non-polar interaction, that is also not good. There should be at least 1 or 2 hydrogen bonds. Then you can have a perfect. Okay. So now, when they say that these HIV drugs, lopinavir and darunavir, they are working, so the question is that you develop this alpha ketoamide. I'm saying that it is better. Whether it is better compared to darunavir or HIV for this HIV. Okay. Well, I mean that you can check. So for lopinavir, the experimentally determined binding energy for SARS-CoV-2 is -6.63. On the other hand, for alpha ketoamide, it is -9 kcal per mole. So that means whatever we have designed it is much better than this lopinavir or darunavir. Okay. So this is one thing. Okay. And then we went ahead and see what are the amino acids, what are the residues from SARS-CoV-3 cell proteins that are mostly contributing to the binding energy. Not all residue form the binding energy, no. So we just decompose the binding energy, and then you can see that for both of these two ligands, these are the residues they are contributing. Now you can see that for A, that corresponds to alpha ketoamide 13B. For that cases, actually, more number of amino acids are contributing by a significant value compared to the other amino acids. So that's why it has a better binding affinity. Now this figure is very important. Now you know that what are the amino acids that are contributing. Now from this one you can actually predict for this inhibitor what mutations can cause drug resistance. For example, M165 that contributes most to the binding affinity. Now if you, so virus are also very intelligent. Generally they have 1 or 2 mutations and then the drug does not work. So if there is a, from this figure you can say that if there is a mutation at the position of M165, then of course there is a high chance that this drug will not work. Okay, so that is also the one thing. Further, this figure also helps you to modify your drugs. Now you know that, okay, these are the amino acids they are contributing most and these are the amino acids they are not contributing favorably. So of course then you know that, and you know the position of your ligand in the binding pocket. So you know that what kind of changes you need to make in your ligand so that it can interact with the amino acids with which it was not previously interacting. Okay, so this figure also, it will help you to optimize your drug further and you can have a better candidate for clinical trial. Okay, so that's one thing. And the second project we are going to talk about, again, also we target this main proteins, okay, through virtual screening, ADMET, and molecular dynamic studies. So generally, this one is started from 1.3 billion compounds, okay. So the strong group, they have developed using a deep learning based method, okay. They call it deep dock, okay. So they make a method. Basically, they incorporate this deep dock with Schrödinger software suite, so that within a reasonable time frame they can do the virtual screening of 1.3 billion compounds, and they did it. And actually, we started from what they got it, okay. So we started from 1,000 compounds that was obtained from 1.3 billion compounds, and then we use stricter method to reduce the number of compounds. And finally, basically, we reduce the compounds to 9 molecules using a glide software, actually, okay? At different level of complexity, we introduce and reduce the number from 1,000 to 9. Now, finally, from 9, we again reduce it to 5 hits by activity analysis and then toxicity analysis, basically ADMET profiling, and all those things. That helps us to reduce the number from 9 to 5 targets. Now, with these 5 targets, we conducted molecular dynamic simulations, performed the structural analysis, and then this MMGBSA that I have discussed previous, we did the same kind of analysis and finally found that there are 4 molecules that has binding energy within 6 to 14, minus 6 to minus 14 kcal per mole. So finally, we have found a compound which is even better than alpha ketoamide 13B. Okay, so these are the glide score of these 9 molecules. Okay, so as you can see, all they are showing a better binding affinity than the alpha ketoamide 13B. But as I told you that this is actually docking score. Okay, so you don't need to believe it as it is. We should verify it via molecular dynamic simulations. And these are all different ADME study, okay? So predicted octanol water partition coefficient, that is log P. So the acceptable range is -2 to 6.5. So all these things I have mentioned here. So I don't want to talk about these things, okay? It's a pretty routine study that you can, so there are a lot of bioinformatics tool available online that you can use it, or you can use any commercial software like Schrödinger also, you can use it, you can get it. Okay, so this actually helps you to reduce the number further, okay? What satisfies, because you need to, the drug should satisfy these ADME properties that you need to make sure. And then you need to study the toxicity also. Then once that is done, then we go ahead and do the structural analysis. Okay, first we need to make sure that, because these are all dog structure, we are not sure whether this ligand will remain in the binding pocket entire time or not. We need to study that thing. Okay, although they are showing very high potential energy, but that's not the case. It may not be the case actually. Okay. So for that one, we conducted MD simulations, and now you can see that for all cases after 30 nanoseconds, they all have reached equilibrium. But there are some deviations that you can observe, which is more than 2 angstrom. Even for the red one, you can see that the deviation is 3 angstrom. Okay. So then we try to calculate the distance between the center of mass of the ligand and the center of mass of the binding pocket, because we want to study whether it is remaining in the binding pocket or whether it is coming out of the binding pocket. Okay, so that's why we measure this distance as a function of simulation time. Now you can see that for molecule E, okay, for the fifth molecule that corresponds to the pink line that you can see after 80 nanosecond, the distance suddenly increases. From 20 angstrom to it reaches to more than 35 angstrom. So it means that in this case, the ligand is not stable. Although you are using one of the best docking software, that is Schrödinger software suite, okay, that is the industry standard software, still their prediction is not that good. In MD simulation, you are saying that it is coming out. It is not stable. Okay, so that are the things, and then C corresponds to the Rmsd of the ligand. Okay, how much they are fluctuating with the things, and then D corresponds to the free energy of the ligand. Okay, basically Rmsd you can plot, of course, one-dimensional potential of main force PMF, basically that you can convert it to energy by using the formula minus RT ln Ki, okay? Sorry, minus RT ln PP is the probability of occurring of a particular conformation. So, okay. So this kind of Boltzmann inversion formula that you can use to convert probability to entropy, energy. So that's exactly what we do. And it shows actually which is the minimum, which is the deviation for which the structure is most stable, that you can see from this figure T, okay? So then we do the binding free energy analysis using the MMPPS scheme, and the results are shown here. And you can see that, like previous cases, we see that the van der Waals VDW term, the first term, okay, everything is negative. That means they are favorable to the binding. And the electrostatic is also negative for all 4 cases. We are not taking into account the fifth molecule because it is coming out of the ligand. So we are not considering, okay. That is also favorable. And then the polar is, as I said, this is a penalty. This penalty, polar solvation free energy, is a penalty that arises due to the dissolution of polar groups, and that always disfavors the complex formation, so it is positive. Okay. And similarly, the non-polar part, well, that is always negative, and that always favors the complex formations. Okay. And entropy minus T delta S, that is also positive, that always disfavors the complex formations. Okay. So the total binding energy, we get it minus, so 27.9, 27.75, minus 34.5, minus 32.5. Okay. So whatever the ranking they predicted from deep dock actually is not correct. Okay. Because we now see that the third one is better than the first one. Okay, so now you understand why do you need to do the MD simulations and use better method to calculate the binding energy. Okay, so you should always supplement your docking study by MD simulation study. That is the best thing. Okay, so that's what it is that you can see that. Okay, so now we found a compound that has a binding energy of minus 14.3 and minus 11.5. 4, 5. So these two compounds are even better than what I showed previously, because that has a energy of minus 9 kcal per mole. So now we have identified two molecules that is even better than that. Okay. So currently we are testing these two in experiment. Okay. So experimental work is going on for these two compounds. Similarly, we found the hotspot residue, that is which are the amino acids that are contributing most favorably to the binding process, and what could possibly be the mutations that can cause the drug resistance. That also you can get it from this interaction spectra. Okay. This is one thing. I don't want to talk much about this. So this one is a different target. Okay. The first two, we talk about the 3-cell protease or the main protease of SARS-CoV-2. And we studied another one. Here we studied even a bigger system. This is actually RDRP, okay, RNA Dependent Rna Polymerase, which is even far bigger molecule. We targeted these things. So it has 3 different subcomponents. You can see the NSP7, NSP8, NSP12, okay. And the binding pocket location is also there. And just I want to tell you that Remdesivir, okay, I think everybody has heard of Remdesivir right now. So Remdesivir actually binds to this protein. The question is, can we find something which is better than Remdesivir? Because Remdesivir was not designed for SARS-CoV-2. No, Remdesivir was designed for Ebola virus. Okay, but since there is some sequence identity and we don't have drugs, so we are using it, and to some extent it is working. So we need to find a drug for this target, okay, for this SARS-CoV-2 only. So basically, we are mostly interested to find out any natural polyphenolic inhibitor that can bind. So that was our interest. Okay, so we take 100 natural polyphenols, and this is the SARS-CoV-2 RDRP, and then we perform molecular docking. So from molecular docking, we get 8 lead polyphenols. Then with those 8 lead polyphenols, we perform MD simulation and then do MMPBS study, then admit prediction, and then target predictions, and then finally we found 4 potential molecules, basically natural polyphenols, that can bind to the SARS-CoV-2 RDRP. Okay, so these are the binding affinity that we obtained from docking study, and for this docking we didn't use Schrödinger. Okay, we used just Autodoc Vina. That yesterday we show you how to use Autodoc Vina, so that we use that free software actually, okay, for this study. Then of course we do that regular study, okay, study their dynamics, whether the code is stable or not, and so all those things we study basically. Okay, I don't want to go into these things. That's not the thing we are interested. So now the main thing is that Remdesivir binds to this protein, okay, and the binding affinity is minus 24.6 kcal per mole. Now, can I find, is it possible that any of the natural polyphenols that can bind to RDRP with a better binding affinity than Remdesivir? Well, I mean, if you look at it, you can see that EGCG, TF3, TF2B, and TF2A, they all are performing better than Remdesivir. Okay, and TF3 is the most potent against RDRP. Okay, and why it is more potent than Remdesivir? That you can get it by comparing each term. Okay, so if you compare the van der Waals term between Remdesivir and TF3, you can see that in TF3 this van der Waals interaction is more negative. That means it is more favorable. However, the electrostatic interaction is also, it is more favorable in the case of TF3 compared to Remdesivir. But the polar solvation free energy, that is more unfavorable in TF3 than Remdesivir. Okay, so overall you can see that the van der Waals interaction and the intermolecular electrostatic interactions are more favorable in TF3 than Remdesivir, causing TF3 to be more potent than Remdesivir. Okay, so that is also another find that we have found, and we reported also this thing is published. We can similarly see that what are the amino acids that take part in the binding process and all those things. Okay, I don't want to talk about it. And these are the hydrogen bond formations. Okay, you can see that remdesivir forms kind of 5 hydrogen bonds, but their occupancy during the simulation is below 20%. Okay. On the other hand, because I said that TF3 is the most potent, now you can see that for TF3 there are 5 hydrogen bonds that form, and their occupancy during the simulation is more than 60%. Okay, so that's why TF3 is found to be better than remdesivir, or TF3 is better than actually other 3 natural polyphenols also. To be honest, actually we are very surprised to get this kind of result. We didn't actually expect. So right now the experimental studies are going on in IIT Palakkad. My collaborator is working on it for the experimental study. Okay, and this is the two-dimensional energy, two-dimensional interaction. So the blue, these green lines, actually dotted lines, corresponds to the hydrogen bond, and this red arc that you are seeing, those corresponds to the hydrophobic interaction. So you can see that actually mostly it is hydrophobic in nature. A lot of residues, they are interacting with the ligand via hydrophobic interactions. Okay. This is the nucleic acid protein. Also, we did some study. Okay. Same thing. We have this. For this one, actually, we docked 20 active compounds of plant extract. Okay. So these 20 compounds were chosen based on their antiviral activity. Okay. So we want to see that whether they binds to the this compound or not. Okay, nucleic acid protein. So here we find that again, as I said, the docking is always not the correct. You can see that for silimarin, it is actually coming out. Okay. If you look at figure B, you can see that the distance between the center of mass of the ligand and the protein is more than 30 angstrom, so it is coming out. Okay. So here also you can see this how they have effect on the atomic motions. Okay, that you can see that. So blue is one that corresponds to the correlated motions, and the red is -1, so that is the anti-correlated motions. So you can see that for hyperserine, it is mostly. I mean, there are a lot of correlated motions up there, but when the ethanolyte D binds to the nucleic acid protein, then you see a lot of red patches. So that means there are a lot of anti-correlated motions are also you have seen that generates. So now when you basically then the study, then you see that ethanolyte has better binding energy than the other 2, hyperserine and silimarin, these 2 natural compounds. Okay, so that means ethanolyte could also be a potential drug candidate. Okay, so this is the final thing I talk about. Here there is no drug binding, rather we have identified another target for designing drug for SARS-CoV-2. We are working on it. This paper is under revision in Frontiers in Biological Sciences, Biomolecular Modeling. Okay. So the 5' capping mechanism of eukaryotic mRNA and some viruses such as coronaviruses are essential for maintaining the RNA stability, protein translation, and for viral immune escape. Okay, and so SARS-CoV encodes SAM, okay, methyl transferase enzyme characterized by NSP16 for generating the cap structure. So the question is, what is the role of NSP10? So they act as a stimulator for the binding thing. So we study that thing. Okay, and so this study is mainly focused on to find a new target, and we suggest that we should not target the NSP16 alone, rather you should target the dimer conformance, heterodimer, NSP16, NSP10, this heterodimer junction is to study to develop a new drug. Okay, for this one we have used very long scale dynamics. We have used 1 microsecond time scale, that is 1000 nanosecond. Previous simulations I showed only 100 nanoseconds, but this one is for 1000 nanoseconds. Okay, And we have studied 3 different systems. One is the complex, so that means that is the NSP16, NSP10 plus the SAM molecule, and then NSP16 plus SAM, and then the NSP10 APO. Okay, so these 3 different we studied, and we see that the NSP10 is very dynamic when it is in APO state, but when they bind, actually the Rmsd actually lowers down, so that means the heterodimer actually. So the binding of NSP10 to NSP16 makes it more stable conformations. Okay, so it gives stabilization to it. And the Rmsf basically, that is the root mean square fluctuations. Basically, it tells you what are the amino acids that are more fluctuating, or what are the amino acids that are most rigid. That thing you can find from it. Actually, from this figure, you can also tell which are the loop region actually, because loop regions are always fluctuating. Okay, so they will have more Rmsf. So from this figure, actually, you can predict. Okay. And then we look at the dynamics of the binding site. So now look at the Rmsd of the SAM molecule, that is figure A. Okay, so we studied it two things. One, when it is bound to the dimer, and when it is bound to the monomer. Now you see that the blue one corresponds to the dimer, and when it is bound to the dimer, and the green ones correspond to when it is bound to NSP16 alone. Now here you can see that when it is bound to NSP16 alone, then the Rmsd is pretty high. Okay, so that's not a good binding. That's not a good sign. But when you target the NSP16, NSP10 heterodimer complex, then SAM has a very low low Rmsd. So it adopts a very stable conformations in the binding pocket. So that will result in a better binding. So this suggests that when you want to target to develop a drug, don't target NSP16 alone. Rather, you should target NSP16, NSP10 heterodimeric complex. Okay. So that's one thing. And then principal component, let's not speak about it. So there are 2 loops actually. Particularly this 2638 loop, that is very important because that resides near the binding site. So you can see that dimerization makes the loop more stable because the Rmsd actually initially it increases, but then gradually it decreases, and from 0.6 microsecond to 1 microsecond, that is the last 400 nanosecond, it is very stable. The same thing we represented in terms of energy, and we found that of course the rate corresponds to multiple minima. You can see that there are a lot of minimas, but the global minima corresponds to an Rmsd of 1.5 angstrom. Okay. On the other hand, when the same molecule binds to NSP16 alone, then it has a higher Rmsd. It is stabilized at 3.4 angstrom. So which one is better? Of course, 1.5 is better. So you should. This suggests that you should target NSP16. Okay. That's all. And then again, the same thing you can represent it in terms of free energy. Okay, so the A corresponds to the complex structure. Okay, so you can see that there is only 1 minima, so that corresponds to a single binding mode. And when you target only the NSP16, then you have 2 minimas. Okay, but the global minima located at 3 angstrom, SAM Rmsd. Okay, and the center of mass distance is around 17.5 angstrom. But the strong binding corresponds to center of mass distance less than 14 angstrom. So it means that that's a weak binding. So it is coming out. So it means that you should not target the NSP16 alone, rather you should target the NSP16, NSP10 dimer to develop a new drug. That is the same thing that you can get from these energy calculations also. Okay, so the same conclusions that you can make from this MMP-based calculations, and we found that it binds with binding energy of minus 6.8 kcal per mole to the heterodimer, and for monomer it is minus 0.6. That means there is no binding actually. Okay, so now this minus 6.8 actually. So when he submitted the paper, at that time there was an experimental result available. So right now there is one paper available in Nature Communications. So they also they predicted, the experimental prediction is the binding affinity would be around -7.3. Okay, and we got -6.8. Actually, it's a pretty good matching with the experimental value. I would say if you consider the error bar that I have shown here, 0.9 kcal per mole. So actually, it's a pretty good matching with the experiment. Okay. And so then we look at what are the amino acids that takes part in the binding and what marks their contribution. So I have also color coded the binding affinity contribution. You can see the color bar actually. Okay. So if you target the complex between the NSP16 and NSP10, you see that more number of amino acids are taking part in the binding. But if you consider only the NSP16 target, then a few amino acids takes part in the binding and their contribution is also good. Okay, so that's why you should target the heterodimer. And this is the hydrogen bond and their occupancy that you can see that if you target the complex, then you have better stability of the hydrogen bond. But if you target the NSP16 SAM alone, then the hydrogen bond actually with the simulation time it breaks down. That's why there is no binding. Okay. And then we look at the protein-protein interactions also, because there are two proteins. First, we study the interaction of the small molecules, SAM with the, so that will act as a drug. Okay, so between that, now we want to study the protein-protein interactions, their dimerization process. So which are the amino acids they are taking part, that you can just look at from the figure A. Okay, and their locations are shown in figure B and figure C. We have shown their locations. And this figure exactly shows the hydrogen bond and the hydrophobic interactions between the amino acids. So as I said, the experimental the result came out lately. So our finding, this is from the computational study, so it exactly matches with the experimental study. Whatever the amino acids we have found are hotspot residue, experiment also support the same thing. But what is interesting, we have studied that what is the effect of temperature on the binding. So everything we are studying at 300 Kelvin temperature. What about if the temperature is suddenly increased to 310 Kelvin? What happens? As you can see here, we calculate the center of mass distance here. Actually, it is coming out. I have shown you the position of the drug molecule, okay, as a function of simulation time at different positions. You can see that actually it is gradually moving away and stays on the surface. So with the increase in temperature, the binding is impaired. Now, what is the effect of salt concentration on the binding? Here also you can see that I told that for stronger binding, the center of mass distance should be less than 14 angstrom. But here you see that initially I started from bounded position. So that's why it is within 14 that you are getting. But with simulation time, it quickly reaches to a value of 18 angstrom. So the binding is significantly impaired. Still it is on the surface, but it's not strongly bound. So that's what I am to talk about, okay? What is the effect? I mean, how can you study the effect of temperature, solvent, the salt concentration on the binding, okay? So all these things will help you to design rational drugs. And generally, this field is very multidisciplinary in nature. You need computational scientists, you need physicists, medicinal chemists, and then biologists. If people from all these different areas come together, then only we can successfully design a drug. Okay, Aaron, you can do anything. Anyway, thank you all, and I really would like to thank you, my student. All the works that I presented is done by these PhD students, so I should thank them. And thank you all for listening. Okay, so if you have any questions, ask me. I'm ready to answer.
Hello.
Yeah.
So thank you, sir. Thank you for your presentation. Now the floor is open for discussion. Any questions from the participants? You can put it up in the chat box, or you can unmute yourself and ask the question.
So Proveen asked, what is Rmsd and Rmsf? So Rmsd is root mean square deviation and Rmsf is root mean square fluctuations, okay? So Rmsd, basically we study with time how your structure is deviating from the initial structure. So suppose you are starting from experimental structure, okay? So how much it is deviated, so that you need to study. Because somewhere your structure should get stabilized, because whatever the properties you want to calculate are equilibrium properties, no? So that's equilibrium thermodynamics. So your system should equilibrate. So Rmsd is one of the things that can tell you whether your simulation has converged or not. Okay, the Rmsf tells you the flexibility of each amino acid. Which amino acid is flexible and how much flexible compared to others. Okay, and then also you can study after the dark binding whether the fluctuation decreases or increases. Those kind of things you can study. So that is very important. I mean, from this also you can clearly tell, okay, this is the loop region. Why? Because there are so high fluctuations. Of course, it has to be loop region. So that kind of thing also you can tell. So like here NSP10 and NSP16, this heterodimer is there. So in their junction, I mean their interface, of course you will see less fluctuations because they interact with each other. They form hydrogen bond. Okay, so their Rmsf value would be less. So if it is less, then you can say that the dimerization is very strong. If you still see some movement there, that means you can tell that they bind weakly to form a heterodimer. That's not a strong binding. Okay, so that kind of thing you can tell. Well, what is your opinion on SARS-CoV-2 is indeed laboratory made or not? To be honest, I don't know. I have no opinion in this regard. But it could be natural. You know, it's not like that. It is highly infectious, but it is not that mortality rate is not that high. It's within 3%, and in India it is even less than 1.5%. Okay, so I believe it is not laboratory made, in my opinion. Okay, I should not tell these things, but anyway. Now, if you look at it, this Chandipura virus or other virus, those are Indian virus. Okay, those are very, very lethal. So Chandipura virus mortality rate is 70%. We are not working on it. There is another virus, KFD, Kynosur forest disease virus. That Kynosur is in Karnataka forest. Okay, so that's a tick-borne virus. So anytime that can attack human, currently they are attacking only the monkey. That is also the mortality rate is very, very high. Then think about the Nipah virus. So we have seen its outbreak in Kerala. Okay, it is far more lethal than SARS-CoV-2. Only difference is that SARS-CoV is very contagious. That is the issue. Otherwise, it's fine. Okay, next.
Any more questions? Yeah, Kim Chili ma'am.
Hello?
Yes.
Yes, ma'am.
Okay. Sir, I have one doubt. So, what is the exact difference between RMS value, RMS velocity, and radius of gyration when we do molecular dynamic simulation? Radius of gyration also is there. So, what is the difference between RMS and radius of gyration?
Radius of gyration basically measures the compactness of your structure. Okay. RMS measures the deviation from the initial structure, and the radius of gyration is used to measure the compactness. How compact is your structure? If the value is too high, that means your structure is unfolding. Okay, so that's you want to. These actually all these things you measure. These are all thermodynamic properties that you measure to ascertain the quality of your simulation. That whatever the parameters that you are using is correct or not. Okay, because you don't want that with simulation time your structure is unfolding. If there is a sudden rise in radius of gyration, it means that the hydrophobic core of your protein is opening up. That should not be. It is hydrophobic. It should not interact with water. Why should it open up? Okay. So those kind of thing you need to check it. For that one, you calculate radius of gyration, and you want to make sure that it is not changing much. It is that value gives you the compactness of your structure. Okay.
Hello. Yes, sir. Any more questions from the audience? So, am I audible?
Yeah, I can hear you.
Yes, sir. Yes, sir. So, so the last person was again our faculty member, Kim Julie, Dr. Kim Julie. She has done her PhD from IIT Guwahati, and she is currently with the biotechnology department. So, on behalf of her and our chair Ram Prakash
Thank you,
Sarma
sir.
sir
Thank
and
you, sir, for your introduction.
Vijay Kumar sir. Yeah, Kimjali madam, you can thank our expert and participants if you wish so. I give the mic to you.
Yes. So actually, my internet connectivity is very bad. That's why I cannot express whatever I want to say also. So thank you so much,
Okay,
sir, for
thank you.
your precious time and your explanation to our doubts.
Yes, sir. So thank you, sir. Thank you on behalf of our director, Professor Dr. Pankeshwar Manta, sir, NIT, and Atal. So on behalf of our chair, Ram Prakash Sharma, sir, and Vijay Kumar, sir. So it's a wonderful session. I hope the participants will take it further. So thank you, sir. Thank you for your this lecture. Thank you, sir. Thank you very much.
Thank you very much. Thank you very much. Okay. Thank you. See you tomorrow.
Yes, sir.
So tomorrow at what time?
So participants tomorrow 9 o'clock, sir. Same. Yes, sir. 9 o'clock, 9 to 10:30.
Okay. Bye.
Yeah, participants, tomorrow will be the last session of sir. So all of you attend tomorrow's session.
So tomorrow we'll talk about coarse grain modeling.
Yeah,
That's
yes.
the one advanced topic.
Yes, sir. Sir, anything informal? If we want to discuss, then I can stop recording and we can have discussion if you wish so. If you have time, you also may be feeling tired.
Yeah. Maybe tomorrow
Actually, if it, okay, sir. Okay, sir. Okay, sir.
on the
Okay,
last
okay.
day, you know, to get feedback and all those things.
Yes, sir.
Okay. Okay.
Yes,
Thank
sir.
you.
So yes, yes, sir. Yes, sir. Okay, sir. Thank you, sir.
Okay. Bye.
Bye, sir.